We're going to talk about here on how we use RocksDB along with Kafka and Kubernetes to build our own distributed database. So I already, P already made an intro, so I'll skip all of these. So just a little bit about Smyte. You know, I guess the audience here knows a little bit more about Facebook than Smyte, so I'll add a few words here. Really, what we're building here is a platform to help our customers to fight all kinds of bad behavior and bad actors on the internet, such as credit card fraud, spam messages, harassment messages, fake campaigns, scams, all sorts of bad behaviors. And it turns out that to find those bad behaviors, a core piece of infrastructure here we want to build is a counter database. We want to count a lot of things in order to tell whether something is bad. Let me give you a few examples. So for example, we want to know how much activities we have seen so far for the given IP, or how many requests that we have received for that IP in the last hour, or for a IPv6 if we want to have a larger address space. Similarly, if we know something, someone is sending requests for signups, we want to know how many signups are from the same single IP in the last hour. Another example would be given a combination of IP and email domain, how many signups have we seen so far? If the count is above a certain threshold, it's likely that someone is creating a lot of fake accounts for same email domain and sending spam messages. Similarly, if we see the same user that is sending a lot of messages that are very similar to each other, then if we have a count for that, we can tell if someone is sending spams in the same way that we use counters for IPs. So to do all that, we just need to build a database of counts. And we are 7 people startup and 5 of us engineers. So we want to build something quick and dirty so that we can build it overnight, and next day we can start pitching our customers, right? So our first choice is actually not RocksDB, but something else. But the goal here is to build a database that has all these nice properties, including replications and fault tolerance, the whole 9 yards, but still want to build it overnight. So our first choice is actually Redis. Right? We already know how to run this. It's very easy to understand. Everything's in memory, and all we want to do is keep some counts for certain keys. How hard can that be? Right? So that's how we got started in version 0. And so here's an example. We received some requests from our customers about IP and a certain point in time. So all we need to do here is bump the count for that IP. But instead of doing that directly, we do a 15 minutes bucket, so that when we ask for IP, a count for IP for the last hour, all we need to do is to do a sum for the last 4 buckets, and we get a rough count of that IP. Now, the problem is, we're not done here, right? The problem is, it's startable and everything's memory, but since we're for the same count, we may need up to 5 buckets to be stored in memory. It's really, really pricey here. But fortunately, we got a lot of credits from generous cloud providers. We got $500,000. So why not just throw money on the problem? And that's what we did, how we built our first version. But as you can see, the buckets are not very accurate, right? So we use 15 minutes bucket. So it's really rough count. But for our problems, we want count to be as accurate as possible so that we can set a low threshold for certain problems so that have a low false positive for our customers. So to do that, let's first look at what we have right now for V0. We solved the problem by having a multiple sharded Redis. We have atomic writes because Redis supports transactions, and it's not hard to do replication in Redis. So we have these, but the rest of it is really hard doing Redis, especially the cost part, because everything is memory. So to solve that problem, we think we really need something that is a real database, and then we found Kafka, which is almost as good as a database because it basically stores a sequential log of messages, which is almost the same as the commit log or write-ahead log for a real database. So what we do here is that instead of writing our accounts directly into our Redis storage, we write that into a Kafka topic with a message like that. You have timestamp and a key. And all we need to do then is to divert the writes like this to Kafka, then have a Kafka consumer that consume these messages and then bump the counts in Redis indirectly. And instead of using 15-minute buckets, now we can bump the count directly using the same key with a prefix about the granularity of the time. For example, here, when we see this message by the Kafka consumer, we can bump the count for the hour and be done with it. And then we can have a second Kafka consumer that doesn't react to the new messages directly, but wait for an hour. An hour later, you could consume the same set of messages, but do the decrements. And all of a sudden, we get almost accurate counts. The difference is only a matter of Kafka delay, which usually no more than a few seconds. And we get fairly accurate count using this approach by simply having a pair of Kafka consumers. And we can extend these ideas using a few more pairs of consumers by having accurate counts for the day granularity every month and weekly and monthly counts. So it's really nice here, but the problem is Kafka only have a limited retention period. For example, to save our cost on storage, we only have 3 days of Kafka messages stored in the cluster. But to solve this problem, fortunately, we back up all our data to S3. So we wrote a Kafka consumer that can seamlessly switch between S3 and the real Kafka cluster, so that for the monthly and weekly counts, we can use the same mechanism, but consume the messages from S3 directly to do the decrements. So that we still get, using the same mechanism, but still get the accurate counts for different time granularities. So at this point, now we get very accurate counts, and sharding is still very easy because Kafka is partitioned naturally, and also very durable because we don't have to worry about losing data in Redis because we can always consume everything back from Kafka or S3. But all our data is still in RAM when we serve this data to our stream processing workers. We have credits, but they're expiring. Before they actually expire or use them up, we need to find a solution that is cheap enough for us to store a lot of data. And before I get to that solution, I want to talk a little bit about the atomicity here. So the idea here that Kafka is offering at least one semantics by default. And we want exactly once because otherwise you might be bumping the count twice or even more when committing Kafka offset may fail. And so the solution to that is quite easy because Redis supports transactions. So you can actually store the count data itself along with the Kafka offsets in the same database so that we get exact one semantics with Kafka. And it's not hard to do it in Redis. Because of that, we also want to find a storage solution that supports the same semantics. And another point I want to make here is that even though we can do replicated Redis, we can have a master-slave backup here, but do the actual operation in production is actually pretty painful, and we have a lot of interesting stories about this. That's another reason why we want to find a more interesting, more scalable storage solution, and that is operationally easier to manage. So finally, I can talk about RocksDB. Right? We want to so that goal here is simple. We want to move most of our count data from memory to disk, but still offer a relatively low latency. Right? We don't have to have extremely low latency, sub-millisecond latency, but relatively low latency is important here for our stream processing workers. And also, we want to make migration really easy because, as you can recall, this is already our third time migrating our data to a different storage solution. In the meantime, we still want to maintain our accurate counts, but we don't, as I mentioned, we don't really need strong consistency. Have a Kafka consumer that is delayed by a few seconds is okay for our use cases, and we don't really need a magical automatic resharding or rebalancing. We did consider, as mentioned by P, we did consider and used a few alternatives, including MySQL and React for this purpose, but they're either too expensive to run or operationally it's not very scalable for a 7-people team to manage on a daily basis. And that's why we choose RocksDB, and we use RocksDB to replace storage, and that's the end of story. But there's a few details I want to mention here. First of all, as I mentioned earlier, we need atomic writes to RocksDB to manage both the account data and Kafka offset. And it's really easy to do that in RocksDB because it supports write batch. And also we can do write batch across multiple column families, which is a very important property that we leverage later that I mentioned in my talk. And secondly, we only have a embedded library for storage here. We need a server solution, and we wrote it in C++ using two other open source library made by Facebook, which give us ability to quickly write the high performance multi-threaded server software in relatively quickly. And all of them is written in C++. The reason why we chose C++ against as opposed to the other fewer fancier language is that, as a matter of fact, we actually tried a few other languages, including Rust, before we went back to C++. The reason is because we want direct binding. The C binding provided by RocksDB is pretty nice, but doesn't have all the advanced features that we wanted in order to have a high performance database. Plus, has the extra, when you read via the C binding, you have at least one extra copy of the data, which really hurt performance here. And so that's the primary reason. And fortunately, because all this nice Facebook library, we managed to do it fairly easily. So as we recall, we still need, even though we use RocksDB, we still need Kafka for durability reasons. So that when you write something, we still write to Kafka first, then have the consumers to consume and write to the RocksDB. And these two systems actually work pretty well, very high performance. For example, when you're playing catch up using Kafka and RocksDB, at one point you can simply easily consume like 10,000 messages in one batch and write that to RocksDB directly using one write batch, which offers really good performance when trying to catch up with a lot of Kafka data. So at this point, this new version, we get all the nice properties except for replication and fault tolerance, which is something that RocksDB doesn't offer off the shelf. So we need to build it ourselves. But we're in the business of building anti-fraud software, not in the business of building distributed database. So we want something that can just work off the shelf. Our choice here is Kubernetes. I think we pretty much used Kubernetes when it was still a beta software, but we really liked it. The idea here is very simple. We want a software that can manage a fixed number of replicas for a certain database, and that's all we need. So the setup here is quite straightforward. At the beginning, we have just one shard. Let's say we have a Kafka topic that's replicated, partition 20, using 20 partitions. And then all we need to do here is that we have this one set of replica, and we want to create a new one. All we need to do is take a snapshot of the existing replicas, just RocksDB files, and using Kubernetes to run it as a second replica. And all we need to do here is just set the second replica up using the existing snapshots, and then start taking from Kafka, because the next Kafka offset that you want to consume from is already part of the data in the database in RocksDB. So all we need to do is start Kafka consumer in a new replica, and as soon as the consumers reaches zero, with zero lag, we're done, and we can start serving the traffic. And really, the nice thing about this setup is that the two replicas, or three, whatever you want to make, doesn't need to know the existence of other replicas. All you need to do is take a snapshot and start consuming from the Kafka cluster. Once you have a set of replicas, Kubernetes provides this feature called cluster IP, which really use IP tables locally on each box in order to help you to balance the traffic across the set of replicas that you have. Now, there's one interesting thing I want to talk about here, is that the conventional wisdom of using RocksDB, or the whole purpose of using RocksDB to begin with, is that you can using this embedded database library to write data locally. But we made this choice early on that we want to write data to a network-mounted or persistent disks, depending on which cloud provider you use. The reason for that is because by using a persistent disk, the operation for managing a database becomes much easier. Imagine we have 20 shards, 20 partitions for a single replica. And what you do, what happens is maybe one of them died because the host machine died, or network partitions, for example. And then all you need to do is have Kubernetes or whatever server framework that you use to allocate a new container on a different machine and move the data by unmount the data from original host and mount the same disk to the new host. Within a few seconds, usually up to a minute, you have the data available and you can start tailing right away, instead of taking another snapshot and catching up with Kafka, which would take much longer time. And the second reason why we choose a persistent disk is because of cost. So at the beginning, as a startup, we have very little data. So we can actually create a very small disk for each partition to begin with. Then slowly, as we get more data, we can resize and add capacity to the disk, and we can do that online using online resizing of EST4. As a result, we can slowly increase our spending on disks without incurring a big upfront cost, which really helped with our operations and cost management. So at this point, using a few off-the-shelf components, we managed to build a distributed database without actually inventing another distributed protocol. And we actually made this system as a framework, and it's because nothing that I talk about today is specific to our counter database. So we made a framework which we intend to open source sometime in the future, and we built a counter database as a special example of that using just a few lines of code. And turns out that the same idea can be applied to many different places by simply replacing the increment-decrement idea with some other operations so that we can have things like key value store or even a search engine by replacing RocksDB with something like Solr. Now, before I wrap up my talk, I want to mention another example that we use the same framework, which is an efficient list store. So the idea here is that we have a lot of entities that we get from our customers, such as IPs, usernames, emails, email domains, etc. And our system would go and label a lot of these things. So for example, for the IP address, we say, hey, this may be a bad IP, and its operations really limited, and there's a lot of signups from this IP that we've seen so far for the last hour. And these, we turn these labels and entities into a list. So we can have a bad IP list of a lot of bad IPs, for example. And the idea here is that we want to store this data structure very efficiently while support high-performance read so that for the given entity, such as IP, we can get all the labels for the given IP. And the idea here is very simple. We can use prefix scanning right off the RocksDB. And so the key here is a tuple of entity ID and list ID. So then given an entity ID, which is just a 64-bit integer, we can do a quick prefix scanning and get a list of all the list IDs, which have the information about all the labels that we can use. And take this idea a little bit further, we also have requirements that we want to expire some of the list or labels on certain entities. For example, we may, when you first saw a user, we give a user label of new user, but we might want to expire it after a week or hour, depending on our customers. In order to do that, we need to have a background job that would periodically modify the data of the list store. The first reaction that we have is there are a lot of job management frameworks that are available, but what we ended up doing is, since we already have a storage and a server software built on top of this database, we can use the database itself to manage the jobs. And the idea is very simple. We use multiple column families here. So the default column family has the list data with the entity list and list ID, entity ID and list ID as the key. But while we're adding a new entity to a default column family, we can also write data to a different column family in the same transaction. And the second column family, we call it scheduled tasks, which is keyed by the expiration time for the jobs. So then the expiration operation becomes very simple. All we need to do is have a thread or bunch of threads scanning the second column families periodically. But because the second column family is sorted by the expiration time, it's really efficient. Just go from the first key up to the key that is no larger than the current timestamp, and we got all the jobs that has expired so far, and apply those operations by writing back to the default column family. However, because the default column family may have other write operations happen at the same time, instead of writing it directly, we apply the merge operator that will read the values for the key and try to merge them together and commit them atomically. So what's interesting here is that it turns out that the merge operator can only merge things, but doesn't support delete. So if we look at two values and decide that result of merge is actually empty data, we cannot ask the merge operator to delete the data. So we also made a simple compaction filter that look at the data and see if the result is empty, just delete the key. It would be nice if RocksDB have this API that allows us also delete the key as a result of the merge operator. So by applying all those advanced features of RocksDB, like prefix scanning, multiple column families, merge operators, and compaction filters, we built a very efficient database that supports range scan and expirations without any external services. So yeah, that's the end of my talk. Any questions? Yeah, exactly. So the question is, when we have one replica goes down, what happens to the user request, right? So the IP tables managed by Kubernetes will automatically update if you retry the request for the client, you would send a request to the available replica. So how much hawk savings we get by moving from Redis to RocksDB? A rough count, I think, P, last time we talked about is like 75%. Is that the magical number? All right. Yeah, so because the high memory boxes in Google Cloud is really expensive. I don't remember exact number. By moving everything into the persistent disk, and then we can use actually very small boxes to run the containers. Yeah, it's I think savings more than like 75%. Yeah. So the question is, I had an example about Solar inside of RocksDB. So the idea is we have this framework where we put all the writes in Kafka. Then there's a consumer that consumed messages and actually do the writes instead of having the writes go directly to the database. So if we replace our RocksDB or Redis database with Solar, then here's the way we build the search engine. We write all the document updates to a Kafka topic, then have the Kafka consumer that consume from the Kafka, and then apply the updates to Solar. And because of that, we get we can also have a replicated Solar cluster that can serve search queries. Thank you.